Hello there, and welcome to The Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into a mystery that sits right at the edge of what reality allows, and sometimes what it seems to forbid. We'll be drifting gently into the strange world where particles slip through barriers as if walls were only suggestions, and the impossible becomes a quiet habit of nature. Before we step into this ghostly landscape of hidden doorways and silent crossings, I'd love it if you could take a moment to like this video and subscribe. Only if these gentle explorations truly feel like a place where you can rest and wonder for a while. And if you'd like, leave a comment telling me where in the world you're listening from and what time the night has reached you. It's always comforting to see all the places we gather from, each wrapped in our own little corner of the dark. Now, feel free to dim the lights, let the air settle softly around you, and let your thoughts loosen. Imagine yourself floating in a warm, dark space, the kind of darkness that isn't empty, but calm, like the hushed glow inside a dream. In this quiet, even the most impossible ideas begin to make sense. Tonight we're going to drift alongside particles that vanish on one side of a wall and appear on the other, moving through barriers they should never cross. And if your mind begins to wander, that's perfectly fine. Just let it drift. We'll be here, following these small, ghost-like footprints across the fabric of the universe. As we begin, allow the world to feel a little softer, the impossible a little closer, and the night a little deeper. Our quiet journey into quantum tunneling starts here. If you close your eyes for a moment and picture a wall, a simple, solid wall, your mind probably brings up something cold and unmoving. Brick, stone, concrete, the kind of surface that pushes back against your hand, firm and definite. We grow up learning that walls stop things, they stop people, they stop objects, they stop motion. A wall says, no farther. It feels like one of those rules reality shouldn't break. But somewhere in the tiny world beneath your fingertips, this rule is quietly ignored. In the space of atoms and smaller things, nature whispers a different story. Particles, little points of existence, smaller than anything you can see, do not always respect the idea of impenetrable. They sometimes appear on the far side of a barrier without ever climbing over it. They don't chip through it, or force their way, or shatter it. They simply show up on the other side, as if the wall were only a thin curtain and the particles slip through the folds. And this is not rare. It's not an exotic event that happens once every billion years. It happens constantly, around you, inside you, within the stars overhead, and the electronics in your pocket, and the biological reactions unfolding inside every cell of your body. The universe depends on these tiny acts of quiet disobedience. For us, as human beings built of countless atoms, the idea feels almost comical. Walking through a wall would require a feat so unlikely that the universe might as well forbid it. If every atom in your body needed to tunnel through a barrier at the same moment, the odds are so low that even if the cosmos lasted far beyond trillions upon trillions of lifetimes, it still wouldn't happen. But for a tiny particle, the world is not shaped by certainty, it's shaped by possibility. And possibility is a landscape far stranger and far softer than the one we're used to. Imagine a tiny grain of dust drifting in a pool of light. Now shrink it down, far smaller than dust, perhaps to the size of an electron. An electron isn't a marble or a speck you can hold in your mind. It's more like a shimmer, a faint cloud of maybe here, maybe there, a small wave of existence spread out slightly in space. When that wave reaches a wall, it doesn't stop abruptly. Instead, it presses into the barrier, fading as it goes, like light seeping into fog. The deeper it goes, the dimmer it becomes, but never fully disappearing. And if a faint trace reaches the far side, the particle can suddenly appear there, as though it's slipped through a hidden passage. This is the essence of quantum tunneling spoken softly. No formulas, no symbols, just a simple truth. The world behaves differently at small scales. The surface that feels solid under your palm is made of forces and electric fields, a tight web of invisible interactions. For a particle described by a wave-like cloud, that web is not an absolute barrier. It's something that can sometimes be crossed. So tonight we begin with a single question. What does it mean for a wall to be solid if the tiniest pieces of reality ignore solidity altogether? When we think of impenetrable barriers, we imagine something absolute. But the universe, it seems, likes to leave small cracks in its rules. Tiny openings where the improbable becomes real. And those openings are not glitches or mistakes. They are part of the architecture of everything. Quantum tunneling is not a failure of physics. It is physics. It is how stars shine. It is how atoms rearrange themselves. It is how electricity moves in certain devices, how memories are stored in digital form, how chemical reactions breathe into motion even in the coldest conditions. But before we explore the stars or the circuits or the quiet chemistry inside living things, we stay here with this wall. A wall you cannot cross, but a particle can. A wall that feels solid, but isn't absolute. A wall that tells us, in the foundations of reality, certainty is replaced with possibility, and possibility reaches farther than we imagined. As we drift into the next moments of our journey, let the idea settle gently. The universe is stitched together not by hard boundaries, but by soft chances, and even the most solid wall has room for a whisper to pass through. If you place your hand against a wall right now, you'll feel something steady pushing back, a firmness that seems unquestionable. The surface will not yield, and your hand will not pass through. It feels like the simplest fact in the world, that solid things are solid, that matter sets boundaries the way stone sets the edges of an old path. This sense of firmness is so normal, so deeply woven into how we understand the world, that questioning it feels almost ridiculous. But tonight, in this quiet space where it's safe to let ideas breathe, we can gently loosen the certainty around that feeling. Because what we call solid is, in the language of the universe, a bit of an illusion built from forces, fields, and waves of probability. And when we look closely, the boundary between solid and not solid becomes surprisingly soft. The first thing worth remembering is that matter is mostly empty space, not metaphorically empty, truly, overwhelmingly empty. If the nucleus of an atom were the size of a quiet pebble resting in your hand, the nearest electron would be orbiting far away like a firefly circling the edges of a stadium. Between the pebble and the firefly lies almost nothing, just stretches of possibility, fields, and the faint shimmer of presence. So why does a wall feel firm beneath your palm? The answer is gentle and a little poetic. You don't actually touch the wall. The electrons in your hand never meet the electrons in the surface. Instead, they lean into each other's electric fields, two invisible landscapes pushing against one another, like the soft repulsion of two magnets that refuse to join. That push becomes the sensation of solidity. In this light, a wall is not a fortress. It is a crowded lattice of atoms, each one with its own swirling cloud of maybe here, maybe there, each one held in place by the quiet tension of forces. When you lean your hand against it, your own atoms feel those forces and stop your motion. But the barrier isn't absolute. It's simply overwhelming for anything as large as you or me. The difference between you and a particle is not just size. It's scale in the language of probability. A particle, something like an electron, does not sit in one place the way we imagine marbles resting on a table. Instead, it exists as a wave of possibility, its presence gently smeared out over space. When that wave meets the wall, it doesn't slam into it like a ball hitting a board. It flows toward it, thins out inside it, and fades. If the wall is thick, the fading is fast. If the wall is thin, the wave reaches the other side with a faint trace of strength, like a whisper slipping through cracks. And this is where the quiet magic of quantum tunneling lives. A particle doesn't break the wall. It doesn't carve a path. It simply follows the shimmer of its own wave, leaking into places that classical intuition would forbid. The particle can appear on the far side because, in the language of possibility, a tiny part of it was already there. To understand why this doesn't happen for large objects like us, imagine your body as an orchestra of countless particles, each one playing its own note, each one with its own faint wave. For you to tunnel through a wall, all of those waves would have to fade into the barrier in perfect synchrony. Every atom, every particle, every subtle vibration. The probability of such alignment is so small that even if the universe were to live trillions of lifetimes, the chance would remain effectively zero. But an electron is not a choir, it is a soloist, a single wave, simple and free. Its story is not drowned out by the mass of a body, or the warmth of biological motion, or the chaotic noise of billions of atoms vibrating together. It can slip its presence into a barrier and appear beyond it because the universe leaves space for small things to act strangely. If we look more closely at solids, we find even more softness. What feels like a rigid structure is actually a dance of balance. Atoms pushing and pulling, stabilizing one another in a silent conversation of charges. In this dynamic world, imperfections arise. Tiny gaps, slight variations in spacing, uneven edges in the energy landscape that define what a particle feels as it approaches. These imperfections can make certain parts of a barrier easier to cross than others. A smooth surface is not truly smooth at its foundations. It is a terrain of microscopic hills and valleys. This unevenness creates subtle pathways. For a particle described by a wave of probability, these tiny differences matter. A thinner region in the barrier becomes a slightly brighter window. A region with less electric push becomes a softer threshold. And so, while the wall is impenetrable for your hand, a particle sees something different. A landscape with a faint glow in the distance. Not an opening exactly, but a place where the fading wave has just enough strength to echo through. As we rest with this idea, the solidity of the world becomes more nuanced. Your table, your floor, the walls and stones and mountains, all the things that feel firm, are knitted from open space and electric whispers. Their stability comes from patterns, not from impenetrability. And patterns, as the quantum world likes to remind us, always leave room for the improbable. This does not make the world less real. If anything, it makes it more beautiful. The firmness beneath your hand is not the result of rigid substance, but the delicate balance of countless tiny presences leaning against each other. The solidity you trust is born from the softness of invisible interactions. Later in our journey, we'll drift toward the mechanisms, the way the wave of a particle thins inside a barrier, the way probability acts as a quiet guide. But for now, it's enough to rest with this gentle truth. What feels solid is mostly empty space, held together by invisible threads. And inside those threads, the smallest pieces of reality quietly slip through walls that appear absolute to us. When we think about moving from one place to another, we imagine a path, a simple, continuous journey. You step forward, you cross the space between, and you eventually arrive. If there's a wall in the way, you either go around it or you stop. That's how motion works in the world we live in. There is a clear route, and you follow it. But in the quantum world, movement is not always a journey in the way our intuition expects. Sometimes it is a quiet rearrangement of possibility. A particle does not walk step by step toward a wall. It leans its presence in that direction, allowing its wave-like nature to seep forward. And because a particle is not a point marching in a line but a small cloud of probability, that cloud doesn't halt at the barrier. It presses into it, thins out, and, in certain circumstances, lets a faint whisper of itself appear on the far side. To make sense of this, it helps to step away from the image of a particle as a little billiard ball bouncing around. Instead, imagine it as a soft glow of presence, something like a candle flame seen through mist. This glow represents where the particle is likely to be found. When the particle is far from any barrier, the glow has a familiar shape, but as it approaches a wall, the glow doesn't stop sharply the way a ball would. It reaches into the boundary, dimming quickly but not completely. This dimming is fundamental to tunneling. The tail of the particle's probability extends into places where, under classical rules, it has no right to be. If the barrier is thick, like a long stretch of stone, the glow fades too quickly to matter. If it is impossibly thick, the effect is so tiny that it may as well be zero. But if the barrier is thin, even just a few atoms thick, then the small fading tail can reach the far side with enough presence for the particle to reappear there. Nothing dramatic happens at the moment it arrives. There's no spark or pop. One moment the particle is mostly on one side. The next moment, it is mostly on the other. The space inside the barrier may contain a faint trace of its presence, but the particle does not carve a tunnel through it. It doesn't break anything or create a path. It merely follows the quiet mathematics of probability, translated here into a soft image rather than equations. We often imagine that a barrier has to be physical and solid, but in the quantum world, a barrier is simply any region where the particle would need more energy than it possesses to enter. In classical thinking, this means the particle cannot go there. In quantum thinking, this means it is less likely to be found there. The difference between never and unlikely is tiny, but in the quantum world, tiny differences are everything. Think of a simple hill in a landscape. If you roll a ball toward the hill and the ball doesn't have enough speed to climb over the top, it rolls back down. That's classical physics. Now imagine that instead of a ball, you have a wave of water approaching the hill. Even if the wave is low, a small splash of water may reach the other side, leaving droplets in a place the ball could never reach. A particle's probability wave acts in a similar way. Where the height of the hill is too great, the wave fades. But a thin region or a narrow ridge allows some part of the wave to spread through. The particle's presence follows that tiny spread. Another way to picture this is to imagine standing before a frosted glass wall. If you place a candle on one side, the glass blocks most of the light, but a dim glow still appears on the opposite side. The candle has not passed through the glass, only its faint radiance has. In tunneling, the faint radiance is the particle's wave-like presence. And if that glow on the other side becomes bright enough in the language of probability, the particle itself can appear there. This is not teleportation. Teleportation suggests instant movement from one place to another, ignoring the space between. Tunneling does not ignore the space. The wave moves through it, fading as it goes. It just doesn't behave in the all-or-nothing manner of classical physics. To a particle, The wall isn't a rigid stop, but a region where its presence weakens dramatically, as though the universe whispers, "You may pass, but only as a faint echo." That echo may vanish within the wall, or it may appear on the far side depending on how thick the barrier is. Because tunnelling depends so heavily on thickness, even a tiny change in a barrier can produce dramatic differences in behaviour. If you imagine a wall carved from one piece of wood, a particle sees it as a barrier of one particular thickness and shape. But if there is a tiny knot in the wood, a place just slightly thinner or slightly less dense, the particle's fading wave can take advantage of that. It can reach across where the wall is narrowest. This is why tunnelling is extremely sensitive to details we cannot see with the naked eye. A barrier that looks smooth to us might be full of unevenness, creating little pockets where particles can slip through more easily. Temperature also plays a role. When things are warm, atoms jiggle. When they jiggle, the barrier changes shape slightly from moment to moment. These fluctuations can allow the probability wave to find moments of easier passage. At colder temperatures, where everything vibrates less, tunnelling sometimes becomes even more significant, especially in chemical reactions. It's a bit like timing your step onto a bridge that sways in the wind. You wait for the moment when it dips in your favour, and you move. Understanding these details tells us something important. Tunnelling is not random chaos. It is structured by the shapes, energies, and patterns hidden in matter. It is the quiet negotiation between the particle's wave-like nature and the subtle features of the barrier. Nothing in this process violates the rules of the universe. Instead, it reveals that the universe has more pathways than our everyday intuition suggests. As we settle with this idea, the vanishing act feels less like a magic trick and more like a natural expression of how the world works at small scales. A particle doesn't defy reality, it reveals a deeper layer of it. A wall doesn't stop everything absolutely, it simply quiets most possibilities. And a region forbidden under classical laws becomes merely unlikely under quantum laws, leaving space for the improbable to become real. The vanishing and reappearing of a particle across a barrier is not an escape. It is the fulfillment of what its wave-like nature allows. A quiet dissolving of certainty, a gentle bending of the rules, and a reminder that the foundations of reality are woven from possibility, not absolute boundaries. If you try to imagine a particle, an electron, a proton, a neutron, your mind may reach for something familiar, perhaps a tiny sphere, a speck, a bead of matter so small it's barely there. This image feels natural. It fits with the way we see the world, made of objects with definite shapes, definite locations, and definite boundaries. But in the quantum world, this picture quietly dissolves. A particle is not a pebble or a grain. It is not a dot waiting to be found at a specific spot. Instead, it is a soft pattern of possibility, spread out like a faint mist, shimmering across a region rather than standing still. To understand tunnelling, and many other quantum mysteries, we must first understand this softness. The idea that a particle behaves like a wave is not a metaphor, it is a statement about its nature. When physicists describe a particle with a wave function, the word itself can sound cold, mathematical, perhaps intimidating. But you can imagine it instead as a sort of luminous cloud, a gentle haze showing where the particle might be, not where it is, where it might be. This cloud has peaks and valleys, bright regions and dim ones, regions of likelihood and regions of near impossibility. Its shape tells us how the particle can behave, and when this cloud leans into a barrier, even one the particle cannot cross by classical standards, a faint trace of the cloud still seeps inside. We can think of the wave function as a lantern glowing softly in a field at night. If you stand far away, The glow is faint. If you stand close, it is bright. In between, the light fades gradually. Now imagine placing a curtain between the lantern and your eyes. The curtain blocks most of the light, but not all. Some of it slips through as a dim, filtered glow. That dim glow is like the presence of a wave function inside a barrier, a fading whisper of probability, barely hanging on, but still real. This cloud-like nature of particles is at the heart of quantum mechanics, and it is this nature that makes tunneling possible. A wave can stretch into places a solid object cannot. It can thin out without vanishing. It can linger faintly where, under classical expectations, it would be forbidden. The particle's ability to appear on the far side of a barrier rests entirely on this wave-like behaviour. But what shapes the wave? What tells it how wide to spread, how quickly to fade, how deeply to seep into a barrier? The answer lies not in formulas, but in the energy of the particle and the structure of the landscape around it. If the particle has more energy, the wave spreads more broadly, like a bright ripple moving across a pond. If it has less energy, the wave stays tighter, more localized, and fades more quickly. The barrier itself, the height that physicists often describe, can be imagined as a steep hill. A taller hill means the wave inside the hill fades more quickly. A shorter hill means the wave keeps more of its strength, and when the barrier is very tall, the wave thins so dramatically that the particle's chance of appearing on the other side becomes astronomically tiny. So tiny that the universe would grow old many times over before such a crossing occurred. But when the barrier is thinner, even just slightly, the wave can pass through more easily. This sensitivity is one of the most striking features of tunneling. A change so small we cannot see it with our eyes can alter the probability dramatically. This is why electrons in certain materials behave in astonishing ways. In some engineered structures, scientists create thin layers just a few atoms wide, barriers so tiny that the electron's wave can seep through them. In these places, the electron's movement is not like a marble rolling on a track. It is more like a vibration finding resonance across a thin film, appearing on one side or the other depending on how the wave aligns. To help this feel less abstract, imagine a room with thick walls on every side. If you whisper, your voice stays inside. The walls trap the sound. But if one wall has a thin gap, even a narrow crack, the whisper may find its way through. Sound waves, like probability waves, seep into spaces where the rules allow even the faintest opening. For particles, the crack in the barrier is not the physical hole. It's the natural thinning of the wave where the barrier is thinner, or the energy landscape is slightly more forgiving. A particle's wave also responds to the environment. At higher temperatures, everything is vibrating. Atoms, molecules, the barrier itself. These vibrations change the energy landscape moment by moment, turning the wall into a shimmering, shifting terrain. Sometimes for an instant, the wave encounters a slightly lower region of the barrier, and in that brief opening, its fading presence can slip farther than usual. At very low temperatures, where vibrations quiet down and everything grows still, something different happens. Certain reactions become dominated by tunneling, because the usual pathways of energy are no longer available. The quiet cold allows the wave function to act more boldly than heat would permit. This interplay between energy, structure, and environment makes the wave-like description both subtle and beautiful. It shows us that the world is not made of rigid pieces, but of patterns that respond to gentle changes. A barrier is not a wall, but a landscape. A particle is not a pebble, but a cloud. And tunneling is the conversation between the two. When a particle approaches a barrier, we might imagine asking, will it cross? But the better question is, how does its wave behave when it meets this terrain? The answer is always a pattern. A bright region on the near side, a fast dimming inside the barrier, and sometimes just beyond the far edge, a faint flare of returning light. That flare is the particle's chance to exist on the far side. Not guaranteed, not forced, simply possible. As we rest with this idea, the world begins to feel different. The wall that felt solid is now a region of interacting waves. The particle that seemed simple is now a shimmering cloud. And the crossing of the barrier is no longer a trick or an exception, but a natural expression of the wave-like nature of matter. Quantum mechanics often seems mysterious, but beneath the mystery lies something gentle, a universe that allows small possibilities to unfold quietly, without fanfare. A universe where presence is not a point, but a pattern, and where a wave fading softly inside a barrier can still find a way through. If you have ever watched fog drift across a quiet field, you may have noticed how it doesn't respect boundaries. It curls around fences, slips through thin cracks between branches, and spreads into spaces that seem too narrow for anything to enter. In many ways, the quantum world behaves with a similar gentleness. When a particle approaches a barrier, it does not collide with it the way a stone hits a wall. Instead, its wave-like presence drifts forward, thinning and fading with distance, until the faintest trace of it reaches the other side. And that faint trace matters. Probability is the quiet architect of tunneling. It determines whether the particle will remain on its side of the wall or appear beyond it. Not by choice, not by force, but by the shape of possibility itself. In the quantum world, each location has a kind of brightness of likelihood, a soft glow that tells us where the particle might appear. When the glow spreads into a forbidden region, even if it is only a dim shimmer, the particle can emerge there. Not always, not even often, but sometimes. And sometimes in the quantum world is enough to build stars, shape chemistry, and define the very structure of life. To understand how probability creates a pathway, imagine again the landscape of a barrier as a hill. A classical object like a marble must climb the hill if it hopes to reach the other side. If it lacks the energy to reach the top, it rolls back. In quantum mechanics, a particle is not a marble, but a wave. As the wave approaches the hill, it does not stop abruptly. It presses into the slope and thins out as it rises. Its brightness fades, not because the particle is losing energy, but because the barrier restricts how strongly the wave can exist there. This fading is not symbolic. It is the essence of what makes tunneling possible. Physicists describe the fading using numbers that drop very quickly with distance. What in mathematics looks like a steep curve that dives towards zero. But instead of writing this curve with symbols, we can think of it as a beam of light shining through a thick fog. The light starts strong. As it enters the fog, it dims rapidly, but it does not vanish instantly. Some of it keeps going, growing fainter and fainter until perhaps only a whisper of illumination remains. If the fog is very thick, the light fades before reaching the far side. If the fog is thin, even the faintest glimmer can emerge. This glimmer is the probability that a particle will appear beyond the barrier. What makes tunneling so remarkable is how sensitive it is. A barrier that is slightly thicker can extinguish the last glow of possibility. A barrier that is slightly thinner can let enough glow slip through. A layer of atoms only a little wider than before can change the tunneling probability by orders of magnitude. A grand shift caused by a microscopic adjustment. This sensitivity is why engineers working with nanoscale electronics must treat the thickness of materials with almost reverent precision. A few atoms more, a few atoms less, can radically alter the behavior of electrons. But tunneling depends on more than thickness. The shape of the barrier matters too. A smooth, uniform barrier creates a predictable fading of the wave, but many barriers in nature and technology are not smooth. They're textured at the atomic level, full of tiny irregularities, regions where the energy landscape dips slightly, forming subtle valleys, or rises gently, forming ridges. These features can act like shortcuts or obstacles for the particle's wave. A slightly lower region is like a dip in the fog where more light gets through. A slightly higher region is like a thicker patch where the glow dims more rapidly. This is why tunneling is never a pure yes or no event. It is a negotiation between the particle's wave-like presence and the landscape it encounters. And because this negotiation happens in a world of delicate probabilities, small differences have enormous influence. Temperature adds another layer to this picture. When a material is warm, its atoms vibrate constantly. These vibrations shift the barrier's shape with each passing moment, like branches in a breeze changing how much fog they let through. Sometimes the barrier becomes slightly easier to penetrate. Sometimes it becomes slightly harder. At extremely low temperatures where motion quiets down, the barrier becomes steady and tunneling behaviors emerge with clarity. Certain chemical reactions, especially those involving lightweight atoms like hydrogen, rely on this quiet. In the cold, the usual energetic routes are closed, so tunneling becomes the main path forward. The reaction proceeds not through force, but through probability. This brings us to a key realization. Tunneling is not an act of defiance. It is an act of permission. Permission granted by the wave-like nature of matter. The particle does not break the rules. The rules themselves allow it to exist in places it should not be under classical thinking. The difference lies not in the particle's behavior, but in the framework through which we interpret it. Classical physics says the particle must climb the hill to reach the other side. Quantum mechanics says the particle is a wave, and waves behave differently. They do not require pathways the way objects do. They explore space as spreads of possibility. If we shift our focus from particles to probabilities, tunneling becomes less mysterious. When the likelihood landscape is shaped a certain way, when the wave fades enough to reach the far side, the particle simply follows where probability allows it to appear. It is not slipping through a secret hole in the barrier. It is following the shape of its own glow. This can feel strangely comforting. The universe is not governed by rigid blocks, but by flexible patterns. Barriers not absolute, but softened by gradients of possibility. Movement is not always a march forward. Sometimes it is the patient drifting of a wave, and what seems impossible from the outside may simply be unlikely within, waiting quietly for the tiny spark of probability to unfold. As we hold this thought, the idea of the impossible grows gentler. A barrier is no longer a command to stop, but a region where presence fades. And a particle is no longer a point locked in place, but a ripple exploring the world with silent insistence. Probability may be intangible, but in the quantum world, it is the closest thing to a pathway. And for the smallest pieces of reality, that pathway is enough to cross even the most forbidding walls. If you ask someone how long it takes to walk through a doorway, they might give you a number, maybe a second or two. If you ask how long it takes a stone to fall, they can answer that as well. Time, in our everyday experience, is something you can measure by watching what moves. A car travels down a road, a leaf drifts through the air, a kettle boils, then whistles. Motion gives time its meaning. But in the quantum world, motion becomes slippery. A particle does not march from one spot to another. It doesn't trace a clear path or follow a single route. Instead, it spreads as a wave of possibilities. Parts of it linger, parts of it fade, parts of it appear elsewhere. So when physicists ask, how long does it take a particle to tunnel through a barrier? the question is much harder than it seems, because under the rules of quantum mechanics, the idea of time spent inside may not be a single, well-defined thing. Yet despite the difficulty of this question, it has fascinated physicists for nearly a century. The barrier is not a place where the particle moves the way a traveller walks through a tunnel. The barrier is a region where the particle's wave dims rapidly, where its presence becomes faint. Asking, how long did the particle spend inside, is a bit like asking how long a shadow spends on the other side of a lantern's glow. The moment you try to measure it, the act of measurement changes the entire situation. Still, physicists have attempted to understand this quiet slipping through. They have created different ways of estimating the delay associated with tunnelling. One approach looks at how a wave changes as it arrives at and leaves the barrier, comparing the timing of its peaks. Another approach tries to track how the wave lingers inside the barrier region. But each method tells a slightly different story, because each measures a different aspect of the wave. None of them capture a single, universal, tunnelling time. We can soften this by thinking of a wave of water hitting a sand dune. Some of the water seeps into the sand, some reflects back, and some emerges on the other side if the dune is thin enough. If we tried to measure how long the water was inside the dune, we would find that the answer changes depending on how we define inside, whether we mean when the wavefront arrives, when the dampening appears on the far side, or how the water saturates the sand. Tunnelling is similar. It is not a clean traversal, but a diffuse fading of presence. One of the most surprising findings in this area is something known as the Hartmann effect. We won't use symbols or equations here, just an image. Imagine you have a wall, and you make that wall thicker and thicker. In the classical world, the thicker it becomes, the longer it should take to cross. If you could sneak through a narrow crack in a wooden fence, it would obviously take longer to navigate a stone wall than a thin plank. But in tunnelling, something strange happens. When the barrier becomes sufficiently thick, the delay time inferred from certain measurements stops growing. Even if you keep thickening the barrier, the estimated delay hardly changes at all. It's as if the wave whispers, beyond a certain point, thickness doesn't matter. The way I fade determines everything. Some interpretations of the Hartmann effect sound, at first, almost magical. They suggest that the effective speed of tunnelling can seem faster than light. But this doesn't violate any cosmic rule, because the wave's faint presence inside the barrier doesn't carry information in a useful sense. It's like the front edge of a ripple moving forward, while the underlying disturbance never actually travels faster than the surface of the pond would allow. The appearance of speed is an illusion created by how the wave reshapes as it interacts with the barrier, not by the particle outrunning reality. To picture this, imagine a row of candles placed behind a frosted glass screen. If you turn them on one by one, the faint glows on the other side of the glass might seem to respond almost instantly, not because the light moved faster than it should, but because the glow is already present as a faint haze behind the screen. The wall does not accelerate the photons, it simply filters them in a way that reshapes the apparent timing. This reshaping is central to tunnelling. The wave of the particle isn't a pulse marching through space, it is a spread out field of possibility. As it encounters a barrier, parts of the wave get reflected, parts thin into the barrier, and parts emerge beyond. The timing we perceive on the far side is not the travel time of a tiny object, but the restructuring of a probability wave. That restructuring can make the emergence appear quicker than intuition would predict. Because the wave fades inside the barrier instead of travelling like a classical object, the particle doesn't experience the barrier the same way we would. To use another image, imagine a traveller walking through thick fog. They move slowly at first, barely visible, but if the fog abruptly thins beyond a certain point, the traveller may appear suddenly clearer. We might mistakenly think they crossed the fog faster than expected, when in fact the fog simply hid their presence for part of the journey. Tunnelling works in a similar manner. The appearance of quickness is woven from how the wave thins and reassembles. Some physicists describe the fading inside the barrier as dwell time, how long a wave lingers in the forbidden region before either returning or appearing beyond. Others frame it as phase time, the shift in the pattern of the wave as it moves through different regions. But even these names are soft metaphors, attempts to put ordinary language around a behaviour that doesn't fit neatly into our usual definitions. The truth is gentler. The quantum world doesn't require particles to move through space the way we imagine movement. A barrier is not a tunnel to walk through, but a region shaped by possibility. Time inside the barrier is not a single number, but a family of ideas, and tunnelling is not a journey measured in steps, but a transformation of likelihoods. If this feels confusing, that's perfectly normal. Tunnelling teaches us something profound about reality. Not everything has one crisp answer. Some questions dissolve when examined closely, like a mist that vanishes as soon as you try to grasp it. Instead of resisting this ambiguity, we can rest in it. The quantum world invites patience, quietness, and an openness to the idea that existence is not always sharply defined. As we let this settle, the debate over tunnelling time becomes not a puzzle to solve, but a reminder of the universe's gentle strangeness. The smallest things do not move the way we do, nor do they obey the boundaries we assume. Their world is made of fading waves, reshaping paths, and subtle timings that evade simple measurement. And within that world, even the notion of time inside the wall becomes a soft and shifting idea. If you step outside on a clear morning and lift your face toward the sky, you feel something warm settling onto your skin, a gentle brightness that has travelled across space for more than 140 million kilometres. It is so familiar that we rarely pause to consider how strange it truly is. The sun burns steadily, day after day, decade after decade, like a lantern that never tires. Its light shapes our seasons, stirs the weather, feeds the green life around us, and keeps our own bodies in balance. Everything we know depends on it. And yet, if the universe followed only the rules of classical physics, the rules of everyday experience, the sun should be dark, completely dark. Not in 1 billion years, not in 10 billion, but from the beginning. The forces that allow its heart to shine are not the forces of ordinary fire or chemical reaction. They come from something far quieter, something that takes place deep beneath the surface, in a realm where particles behave like soft waves of possibility. If not for quantum tunnelling, the sun's core would be a cold, silent ocean of hydrogen, frozen in potential. Life, light, warmth, none of it would exist. To understand why, imagine the centre of the sun as a vast and crowded furnace. The temperature there is unimaginably high, millions of degrees, with particles moving fast enough to crash into one another constantly. But temperature alone is not enough to force the sun to shine. For 2 protons to fuse and begin the chain of reactions that create light, they must come close enough that the strong force, the glue that holds atomic nuclei together, can pull them into a single united state. But protons repel each other strongly because they both carry positive charge. It's as if 2 magnets with the same pole are floating in a boiling sea. No matter how turbulent the water, they never touch. Classical physics says the energy required to overcome this electric repulsion, the hill the protons must climb, is far too high for the sun to ever achieve. The protons simply don't have enough speed, even in the searing heat of the core, to climb over that barrier. And here is where the quiet magic appears. Quantum mechanics tells us that a proton is not just a point of charge. It is a wave of possibility, a shimmering cloud of maybe here, maybe there. When one proton approaches another, its wave does not stop at the barrier of electrical repulsion. The wave presses into that forbidden region, thins out, fades, yet never goes completely to zero. A faint whisper of its presence seeps through the barrier. If the barrier were thick, that whisper would die almost instantly. But in the heart of the sun, where conditions are dense and energies high, the barrier is thin enough for that whisper to matter. And sometimes, just sometimes, that fading glow ends up on the other side of the barrier, in a region where the strong force can grab hold and pull the protons together in an instant of fusion. This is tunneling at its most dramatic. The moment a proton appears inside the forbidden zone, not by climbing over the barrier, but by letting its wave seep through it. It does not violate the rules of the universe, it reveals a deeper rule. Underneath the iron laws of force and distance lies a quieter truth. Possibility flows even into places that seem unreachable. If we imagine the sun's core not as a raging ocean of heat, but as a place filled with waves that constantly overlap, interfere, fade and reappear, its brightness begins to feel like a gentle miracle. Each fusion event is a moment where probability is allowed to express itself, and each moment releases a tiny spark of energy that eventually rises through the sun's layers, scattering, softening, bouncing among atoms for thousands of years before it escapes as the warm light touching your face. To make this feel more real, picture two people trying to come together in a crowded room. In classical thinking, they can meet only if they physically pass through the crowd, pushing, weaving, finding a clear path. But in the quantum world, the crowd is a probabilistic barrier. Sometimes without either traveller forcing their way, the lines of possibility shift and the two people find themselves beside one another. It's not that they push through the crowd, it's that the shape of the crowd allowed the faintest path to open. This faint path in the sun is enough to ignite stars. The sun shines because in every second, countless trillions of protons quietly slip through the barriers that should hold them apart. These ghostly crossings power the chain reactions that create everything from sunlight to starlight, from solar winds to the warmth in your home. And this is not unique to our sun. Every star in the universe depends on the same subtle mechanism. Tunneling is the engine of starlight, the hidden breath of cosmic furnaces. Without it, the night sky would be empty. Galaxies would be dark spirals of cold gas. Planets would be frozen, barren worlds drifting in silent interstellar shadows. No chemistry complex enough to sustain life could unfold in darkness this complete, and the delicate arrangements of atoms in your body would never have formed at all. So when we say that the sun shines because particles cheat the rules, we do not mean they break anything. They follow a deeper order, an order built from waves, not points, from possibilities, not certainties. The fusion at the heart of the sun is a quiet reminder that the universe allows small things to do improbable things, and that these improbable things, repeated tirelessly over cosmic timescales, create the world we know. And now, as you sit in the calm of this moment, you carry a piece of that improbable radiance inside you. Every atom heavier than hydrogen, carbon, oxygen, calcium, was forged in a star by processes that relied on tunneling. Even the light reaching your room now has its origin in a ghostly crossing that happened long before it ever touched your skin. The sun is bright not because nature is forceful, but because nature is subtle. It shines because particles whisper through walls that should stop them. It shines because possibility is allowed to bloom even where certainty would forbid it. and it shines because the universe, at its deepest level, is shaped by quiet miracles. If you hold a piece of ancient rock in your hand, something taken from a mountain cliff or the bed of a river, you're touching a quiet story written over billions of years. That story is shaped not just by wind, water, or tectonic force, but by subtle quantum events happening inside the atoms themselves. Events so small, so improbable, and so ghost-like that they unfold unnoticed, one particle at a time, gradually changing the matter around us. This slow reshaping is radioactive decay, and at its heart lies quantum tunneling. Radioactivity may sound dramatic, even dangerous, but in its gentlest form, it is simply the universe adjusting itself in tiny steps. In certain heavy atoms like uranium or thorium, the nucleus is packed tightly with protons and neutrons. It is a little like a room crowded beyond comfort. Everything is held together by the strong force, that deep and binding glue of nuclear physics, while at the same time being strained by the push of positive charges that repel one another. These conflicting pressures create a situation that is stable, but only barely. A kind of tension lives inside the nucleus, silent but persistent. Among the ways this tension releases is through something known as alpha decay. An alpha particle, made of 2 protons and 2 neutrons, sits trapped inside the nucleus. Classically, it cannot escape. Around it rises a wall of electric repulsion. Think of this wall as a steep hill made of pure pushback. The positively charged particles outside the alpha cluster repel it strongly, creating a barrier far taller than the alpha particles' available energy. If we relied only on classical physics, this hill would be impossible to climb. The alpha particle should remain caged forever, and yet after minutes, hours, years, or even millions of years, the alpha particle slips out. Not by breaking the barrier, not by overpowering it, but by tunneling. Inside the nucleus, the alpha particle exists not just as a cluster of matter, but as a wave of probability, a gentle smear of where it might be found. That wave presses against the inner wall of electric repulsion, thinning and fading into the region just beyond. Inside the barrier, the wave becomes incredibly faint, but not zero. The electric hill may be high, but its edges are not infinitely thick. And because the wave fades gradually, like light moving through fog, a tiny part of it reaches the other side. When that faint whisper appears beyond the barrier, the alpha particle has a chance to suddenly be found outside. At that moment, decay happens. If the wall were thicker, the wave's whisper would die out before reaching the far side. If the wall were thinner, if the shape of the nucleus changed subtly, the whisper would grow stronger. This sensitivity is why radioactive decay has such varied lifetimes. Some isotopes decay in fractions of a second. Others take billions of years. Each lifetime is shaped by how the wave thins, how the barrier resists, and how probability finds its path. To picture this, imagine a bird trapped in a glass dome. The bird cannot break the glass, cannot push it open. But imagine that the glass, though solid, grows thinner toward the edge. At one spot, it is delicate enough that the faintest breeze could pass through. The bird itself cannot pass, but its presence, its call, its flutter, might create a tiny echo on the far side. And if we treat that echo as the particle's wave, then the moment the echo becomes strong enough to register, the bird appears outside. It has not broken the dome. It has simply found a place where the boundary is thin enough for possibility to flow through. This is how heavy atoms unravel, not through explosions or violent tearing, but through the quiet seepage of probability. One alpha particle slipping free at a time, and this quiet unravelling shapes the world in ways both subtle and profound. In geology, radioactive decay acts as the universe's clock. By measuring the ratio of parent atoms to daughter atoms in a rock sample, scientists can estimate how much time has passed since the rock solidified. This method, radiometric dating, relies entirely on predictable tunneling events. When we say a rock is 3 billion years old, we are reading the traces of countless tiny escapes that happened inside its atoms over that vast span of time. Each escape was a single moment of tunneling, a probability realized in silence. In archaeology, carbon dating works in a similar way. Carbon-14, formed in the upper atmosphere, mixes into living organisms while they breathe and eat. Once an organism dies, the carbon-14 inside it begins to decay, releasing beta particles through another quantum process. By measuring how much remains, we can estimate the time since death, a story written by the slow fading of possibility inside carbon atoms, and at a cosmic scale. Radioactive decay helps shape the evolution of planets. Deep within Earth, the heat that keeps the mantle flowing and the crust shifting comes partly from radioactive decay. The drifting continents, the slow rise of mountains, the molten core that protects us with a magnetic field, these are kept alive by tunneling events happening in atomic nuclei scattered throughout the planet. Even the auroras that dance in polar skies trace their origins to a planet warmed, in part by particles quietly slipping through barriers millions of times every second. All of this, geology, archaeology, planetary evolution, comes from a mechanism so gentle it almost feels poetic. A particle sits in a deep well, presses against the wall, and slowly, grain by grain, the universe shifts. Nothing breaks, nothing shatters. Instead, the world changes through the faintest glow of possibility. A nucleus lets go of a piece of itself. A rock keeps time. A planet warms. A story unfolds across eons. If we step back for a moment, radioactive decay becomes less a frightening process and more a cosmic sigh, a release of tension woven into the structure of heavy atoms. And at the centre of that process lies tunneling, a reminder that even the strongest barriers are not absolute, and even the most tightly bound systems contain pathways for quiet transformation. Inside every handful of soil, inside every mountain, inside every living body, alpha particles are being released through tunneling, gently reshaping the world without noise or force. The universe unravels not in sudden ruptures, but in countless soft steps, each one guided by the wave-like nature of matter and the delicate rules of probability. If you sit quietly for a moment, just breathing, listening to the soft movements of your own body, you might feel as if nothing particularly mysterious is happening inside you. Your heartbeat is steady, your breath rises and falls. The air in the room feels gentle and familiar. It is easy to imagine that your body is a world governed entirely by chemistry as we learned it in school. Molecules colliding, reacting and rearranging themselves according to well-defined rules. But beneath that calm rhythm, hidden far below the scale of your senses, your cells are humming with an astonishing subtlety. Enzymes fold and unfold, passing molecules from one state to another. Proteins bend like intricate sculptures. DNA unwinds and rewinds in quiet cycles. And within this microscopic choreography, something even more delicate is unfolding. Something that looks strangely similar to the tunneling we've seen in stars and radioactive atoms. Inside you, tiny particles perform ghost-like journeys every second. Hydrogen atoms slip through barriers too high for classical chemistry. Protons reposition themselves through impossibly narrow passages. Electrons take shortcuts that no classical path would permit. These are quantum tunneling events, woven into the very fabric of life. To understand why tunneling matters in biology, imagine a chemical reaction taking place inside a warm drop of water. In classical chemistry, a reaction proceeds when molecules collide with enough energy to climb over an energy hill, a barrier that separates reactants from products. If the molecules do not have enough energy, they cannot pass, and the reaction stalls. But the body often relies on reactions that would be impossibly slow or difficult if every molecule had to climb the hill. Enzymes help by lowering these hills, shaping and guiding molecules into positions where reactions can happen more easily. But even with this help, some reactions remain important yet classically improbable. And this is where tunneling steps in. Hydrogen, being the lightest of all atoms, often behaves in ways that blur the line between classical and quantum behaviour. Its nucleus, a single proton, is small enough that its quantum wave spreads appreciably. When a reaction requires that proton to move from one part of a molecule to another, the proton does not always need to climb the energy hill separating those two spots. Instead, its wave-like presence presses into the barrier, fades gently, and sometimes reappears on the far side. The reaction proceeds not because the proton overcame the hill, but because its wave slipped through it. In the language of chemistry, we call this proton tunneling, but in the language of imagery, we might say it is like a small spark of presence drifting through a narrow gate that seemed locked from the outside. This process is not rare. It happens in enzymes that regulate vital reactions in metabolism, in DNA repair, in photosynthesis, and in the breakdown of nutrients. Even the way certain molecules in your nose respond to scents may involve electrons tunneling in response to the shape and vibrations of odour molecules, a theory that evokes the idea of smell as a quantum-assisted sense. To make this feel less abstract, imagine a violinist tuning their instrument in a quiet room. The slightest shift in string tension can produce a new note, something fragile, unexpected, and beautiful. Biological tunneling behaves in a similar way. The slightest shift in the structure of an enzyme, the tiniest change in temperature or alignment, can create a new pathway for a proton or electron to slip through. This sensitivity is one reason tunneling becomes especially important at low temperatures. In cold environments where molecular motion slows and classical pathways shut down, tunneling can carry reactions forward. Certain organisms, like those living in deep oceans or frozen landscapes, depend on reactions that remain active even in the cold. Tunneling gives life a way to keep moving when energy becomes scarce. It is a small, hidden breath that keeps processes alive. Some researchers even suggest that tunneling may have played a role in the earlier stages of life on Earth. Before enzymes evolved, before cells existed, simple molecules drifted in ancient oceans, reacting only when conditions allowed. In such uncertain environments, tunneling could have enabled delicate reactions to happen at rates just high enough to maintain momentum. It might have given early chemistry the gentle push needed to form more complex structures, which eventually led to primitive forms of life. Perhaps this is why many scientists speak of tunneling in biology with a sense of reverence. It is subtle, nearly invisible, woven into processes that must be both precise and dynamic. It is not a dominant force, nor a dramatic one. It is a whisper, a faint glow passing through a molecular barrier, guiding reactions in ways that classical physics alone cannot explain. If you could watch your cells with quantum-sensitive eyes, you might see countless tiny flickers of possibility, protons and electrons slipping through narrow corridors of molecular structure, as if each molecule contained a hidden hallway known only to these smallest travellers. Every second, trillions of these ghost-like jumps unfold inside you. Each one is small, but together they sustain the chemistry that keeps you alive. And so, when we say that the universe depends on tunneling, we do not mean only stars or radioactive atoms. We mean you, your cells, your breath, your heartbeat, your thoughts, Quantum tunneling is not just a cosmic phenomenon, it is a biological one. It participates in the quiet work of enzymes, the delicate flow of energy, and the subtle choreography of molecules inside every living organism. It is a strange thought that life depends on particles doing things they should not be able to do. But in the quantum world, the boundary between should not and sometimes do is thin and forgiving, and through that thinness, the improbable becomes essential. If you place a hand over your chest and feel the steady rhythm there, you are feeling the result of a chain of reactions guided in part by tunneling. If you breathe in gently, you're sensing the product of countless molecules that move through barriers too narrow for classical motion. And if you sit quietly and reflect on your own existence, you're carried by reactions that rely on the smallest echoes of possibility. Inside you, at this very moment, the quantum world is alive, subtle, silent, and essential. If you've ever leaned close to a painting in a museum and seen the brush strokes up close, the tiny ridges, the delicate grains of pigment, you know the feeling of witnessing detail that usually stays hidden. Most of the world lies just beneath the limits of our eyes, and even under a microscope there is a point beyond which everything blurs. Atoms, those building blocks of everything you've ever touched or seen, are far smaller than light itself. No ordinary microscope can show them to us. For centuries, scientists could only infer their existence through indirect signs, like detectives reading footprints rather than seeing the creature that made them. Then, in the 1980s, something remarkable happened. A new kind of instrument was created, one that didn't rely on light or lenses or magnification. Instead, it used quantum tunneling, this ghost-like slipping of particles through barriers to let us touch atoms without actually touching them. This instrument was the Scanning Tunneling Microscope, or STM, and it works by listening to the faintest whisper of electrons tunneling through empty space. To imagine how the STM works, picture a needle so sharp that its very tip ends in a single atom. This needle is brought incredibly close to a surface, so close that the gap between them is only a few atoms wide. But it never actually touches the surface, it hovers just above it, like a feather held over a table without quite settling down. In the space between the needle and the sample lies a narrow barrier, a tiny vacuum gap, a space where electrons should not cross under classical rules, but they do, and they do so through tunneling. When the needle is close enough, electrons leap across the gap not by force, but by possibility. A faint tunneling current appears, a soft stream of presence that depends entirely on how close the needle is to the surface. And here is the most astonishing part. This tunneling current is unimaginably sensitive. If the needle moves closer by even a tiny fraction of a nanometer, a distance so small it's like lowering your hand by a single grain of smoke, the tunneling current increases dramatically. If the needle lifts ever so slightly, the current almost vanishes. It's like holding your palm near a candle flame. Even the smallest shift changes the warmth you feel. This sensitivity gives the STM its power. By scanning the needle gently across the surface, measuring the tunneling current at each point, the instrument creates a map of the surface, a map drawn from probability, not touch. What emerges is an image of atoms arranged like beads in a pattern, or bumps on a landscape. You can see every hill and valley, every ridge, every gap. You are, in a sense, running your fingertip over the atomic fabric of matter, guided by a current made of electrons slipping through the vacuum. It is hard to capture just how extraordinary this is. For the first time in history, humans could see individual atoms directly, not as abstract symbols, not as theoretical concepts, but as actual structures with shape and position. The world became more tangible and more dreamlike at the same time. If we visualize this process, we might imagine the needle as a curious traveler walking through a dark forest with only a tiny lantern. The lantern light doesn't reach far, but it reveals whatever lies closest. As the traveler moves, the lantern flickers differently depending on what is near. The tunneling current is like that flicker, a delicate sign that tells us what the needle is passing over. But the STM can do more than see atoms. It can move them. Because the needle's proximity can nudge atoms ever so slightly, like a fingertip nudging a grain of dust on a smooth table. Scientists can use the STM to pick up and place individual atoms. They can build tiny patterns, write letters, create quantum-scale structures. In one of the most iconic demonstrations, a team arranged atoms into the shape of a smiley face, reminding the world that even at the smallest scales, science can carry a hint of humour. This ability to manipulate single atoms opened an entire field, nanotechnology. Researchers can study how atoms behave when arranged in new patterns, how electrons tunnel in confined spaces, how surfaces change when altered one piece at a time. And from these studies came new paths toward data storage, new materials, and the early hints of devices that harness quantum behaviours directly. But behind all of this, every image, every atomic structure moved, every surface mapped, lies tunneling. If electrons could not seep across the vacuum between the needle and the surface, the STM would be blind. It would feel nothing, like a hand hovering too far above water to sense its warmth. Tunneling is the bridge, the quiet crossing that links the tip of the needle to the atoms below. To appreciate the sensitivity involved, imagine a door that opens only when a whisper is spoken at exactly the right distance. Too close, and the whisper becomes a shout that startles it shut. Too far, and the whisper never reaches. Only at a particular distance does the door respond. STM works within that fragile balance, listening to the fading and rising of electron presence across the vacuum. In a way, the STM is the purest expression of tunneling in technology. It is not using tunneling as a side effect, or an inconvenience, or a complication. It is using tunneling as its main sensory organ, its eyes and fingertips combined. It proves that something as intangible as probability can be turned into a tool, something that reveals the hidden architecture of matter with extraordinary clarity. When you see an STM image, a grid of bright spots marking each atom, you're looking at a portrait drawn by electrons crossing impossible gaps. Each point on the map is a place where tunneling occurred, where the needle listened closely enough to hear the whisper of electrons slipping through the barrier. And that whisper tells us about the structure of the universe at its smallest scales. So much of human touch is blunt. We push, we press, we grip. But at the atomic level, touch must be redefined. Becomes a matter of distance, sensitivity, and the gentle flow of probability. The STM teaches us that even without direct contact, you can reach out and perceive something as delicate as a single atom. In the quiet world beneath our senses, tunneling becomes a sense, an awareness, a way of perceiving. And through it, we have learned to explore the edges of reality with a needle that never truly touches, guided by the faint glow of electrons moving through what should be an impossible barrier. If you look at a modern computer chip, it resembles a tiny city, dense networks of pathways, layers stacked with astonishing precision, billions of transistors arranged in patterns finer than a grain of sand. These transistors act like microscopic switches, controlling the flow of electrical signals that make every program, every app, every pixel of your screen come alive. For decades, engineers have been shrinking these switches smaller and smaller, chasing a dream of packing more computing power into smaller spaces. This shrinking has shaped our digital world, giving rise to smartphones, satellites, supercomputers, and systems that can process unimaginable amounts of information. But there is a quiet limit hidden inside this progress, a limit rooted not in engineering challenges, but in the subtle rules of the quantum world. To understand this limit, imagine building a wall out of layers of bricks. As long as the wall is thick, nothing passes through. But if you keep making it thinner, removing bricks one by one, eventually the wall becomes fragile. It may still look like a wall, but it no longer functions as a true barrier. Something similar happens with modern transistors. A transistor works by controlling whether electrons can pass through a region, whether the pathway is on or off. For the off state to work properly, electrons must be blocked by a thin insulating layer, often made of a material like silicon dioxide. For many years, engineers made this insulating layer thinner and thinner to improve performance. A thinner layer meant quicker switching, lower power consumption, and more transistors in the same area. But as the layer approached just a few atoms in thickness, the world of classical physics began to give way to the world of quantum possibilities. At such tiny scales, electrons no longer see the insulating layer as a strict barrier. Instead, they sense it as a narrow region where their wave-like presence can fade but not vanish. Their probability cloud presses into the barrier, and in some cases, a faint part of that cloud reappears on the far side. The electron tunnels through the insulating layer, not because it has enough energy to cross, but because its wave can seep through the narrow space. For the transistor, this is a disaster. The switch that was meant to be off is no longer fully off, it leaks. To make this idea feel tangible, imagine a house with thin walls. When the walls are thick, sounds from outside are muffled or silenced. But if the walls become paper thin, a whisper on the other side can slip through. Transistor barriers that once blocked electrons completely now behave like thin paper. Even when closed, they allow a quiet leak. This leakage causes heat, wastes power, and makes it harder to maintain the clean, sharp signals needed for reliable computing. In early generations of chips, leakage was so small as to be irrelevant, but as transistors shrank to the scale of nanometers, billionths of a meter, the problem grew. Engineers began encountering a phenomenon known as tunneling leakage, where electrons would appear on the wrong side of the barrier simply because the barrier had become too thin for probability to be contained. This effect doesn't break the transistor in a dramatic way. Instead, it introduces a whisper of chaos, tiny misfires, small errors, and the steady warming of the device. If not controlled, these whispers accumulate and degrade performance, like small cracks that spread quietly through a foundation. To counter this, engineers invented new materials, high-K dielectrics, which create thicker effective barriers without sacrificing performance. These materials act like sturdier walls, providing the electron with a taller hill to face, so its fading wave loses strength more quickly inside the barrier. By shaping the barrier more cleverly, they restored the ability of electrons to be cleanly switched off. But even these advancements are temporary. The quantum world always waits at the horizon of progress. Some researchers believe we are approaching the smallest practical size for classical transistors. Beyond this, tunneling becomes too dominant to ignore. Like water finding its way through the thinnest cracks, electrons will continue to slip through barriers once thought impenetrable. This is why the future of computing may require entirely new architectures, designs that work with quantum effect rather than against them. One such idea is the tunneling transistor, a device that intentionally uses tunneling to switch states more efficiently. Instead of fighting the phenomenon, it channels it. In a tunneling transistor, the on state occurs when the particle's probability wave aligns with the barrier in a way that allows tunneling to happen readily. The off state occurs when the wave is positioned so that tunneling is unlikely. Such devices could operate with lower power, and may help extend the limits of chip miniaturization. Another path points toward quantum computing, where tunneling and other quantum behaviors are harnessed directly to perform tasks classical computers cannot. But even there, tunneling can be both a tool and a challenge. It can help qubits change states, but it can also cause them to decohere, to lose their delicate quantum information, if not controlled with extraordinary precision. The story of transistors and tunneling is, in many ways, the story of humanity learning when to push forward and when to listen. For decades, we pushed towards smaller, faster, denser designs, and tunneling whispered warnings that we were approaching a boundary. But instead of stopping innovation, this whisper opened new directions. Engineers began to explore new materials, new designs, and new ways of thinking about computation. This is the quiet paradox. Tunneling can both break our devices and inspire entirely new ones. It can disrupt an established technology while opening the door to another more powerful technology beyond it. It is both a challenge and a guide, pointing toward a future where the quantum world is not a barrier to progress, but the foundation of it. If you think about your phone, your laptop, your smartwatch, every device that lights up your day, you're holding the result of humanity's long conversation with electrons. We have learned to guide them, block them, and channel them. But at the smaller scales, we cannot fully command them. We can only shape the terrain and let their waves respond. And when those waves slip through barriers, we see both the limits of our designs and the beginnings of something new. Tunneling teaches us a quiet lesson. Progress is not always about force or speed. Sometimes it's about listening to the soft boundaries that nature sets, understanding when walls become too thin to hold back possibility, and discovering new ways to work within those boundaries. If you've ever walked into a room at night and turned on a light, the electricity that brightens the space seems simple, something that just happens quietly and reliably. But beneath the surface of that ordinary moment lies a world of electrons weaving through metal wires, scattering, bumping into atoms, losing energy as heat. This scattering is why so many devices warm up during use. It is the unavoidable friction of everyday electricity. Now imagine a world without that friction. A world where electric current flows with perfect grace, no heat, no loss, no resistance. A world where electrons move as if gliding across ice so smooth that nothing can slow them down. This is the world of superconductivity, and it arises when matter enters a deeply strange quantum state. Inside that state, electrons do something extraordinary. They pair up and behave not like countless individual particles, but like one united wave. And through that wave, tunneling takes on a role we rarely see, one that bridges the microscopic and the macroscopic, creating effects you can see with your eyes. To understand this, let's imagine electrons under normal circumstances. In a metal at room temperature, electrons scatter constantly. They bump into atoms, get deflected by impurities, and lose part of their energy along the way. It's like trying to run through a crowded marketplace. You may eventually reach the other side, but not without slowing down, bumping shoulders, and leaving a trail of energy behind you. Superconductors change the marketplace into a quiet, empty field. When certain materials are cooled to extremely low temperatures, the atomic lattice becomes calm and organized. Vibrations fade, motion quiets. In this stillness, electrons begin to interact with the lattice in a new way. Instead of scattering off vibrations, they form gentle pairings with one another, pairs known as Cooper pairs. You can imagine a Cooper pair as two dancers who move together effortlessly, gliding across the floor with perfect coordination. As long as the music, this special quantum state, continues, they remain bound in motion that cannot be easily disturbed. The most remarkable part is that these pairs don't just move through the superconductor. They move as a single, connected wave, the same kind of wave of possibility we've discussed throughout this journey. But here, the wave is not the size of an electron. It spans a scale large enough to see with specialized instruments. This is one of the rare places in physics where quantum behavior shows itself on a scale big enough to touch, big enough to measure with macroscopic devices. What we are witnessing is macroscopic quantum tunneling, an entire ensemble of electrons behaving like a single entity, slipping through energy barriers that would stop individual particles cold. To picture this, imagine a choir singing a long, sustained note. If each voice sings alone, the sound is fragile, easily interrupted by a cough, a mistake, a shift in breath. But when many voices sing together, perfectly aligned, the note becomes stable, resonant, powerful. A Cooper pair wave behaves like a unified choir. It does not lose energy easily, it does not stumble, and when it encounters a barrier, like a thin insulating layer between two pieces of superconducting material, it can tunnel through as one. This is the phenomenon behind the Josephson junction, named after the physicist who first predicted it. A Josephson junction is a tiny sandwich. Superconductor, insulating layer, superconductor. The insulating layer is so thin that electrons should not pass through it in a classical sense. Yet when the material enters its superconducting state, the paired electron wave presses into the barrier, fades, and reappears on the other side, allowing a current to flow with no resistance. It is tunneling not of one electron, but of countless electrons acting together. You can imagine the insulating layer as a narrow stream cutting across a field. A single person might struggle to leap across, but a tightly coordinated group, a line of dancers holding hands, might sway forward together, letting their shared balance carry them over the water in one fluid motion. The leap is not a forceful jump, but a gentle arc made possible by unity. This macroscopic tunneling is not only beautiful, it is useful. In fact, it is the foundation of superconducting quantum computing. Each Josephson junction acts as a tiny element that can store and manipulate quantum information. Instead of relying on classical bits, zeros and ones, these superconducting circuits use quantum states that can be both at once, or somewhere in between, with delicate mixtures of possibilities. These quantum bits, or qubits, allow for forms of computation that exceed what classical computers can do because they explore many pathways of probability simultaneously. To make this concrete, imagine a qubit as a small valley between two hills. A classical particle must choose one hill or the other, but a quantum particle, or in superconducting qubits, a quantum wave of Cooper pairs, can exist in a gentle mixture of both hills at once. Tunneling is what allows the wave to drift between them. This drift becomes the basis for computational operations, not forceful jumps, but quiet, probabilistic shifts that encode information. However, this sensitivity also means qubits are delicate. Any disturbance, heat, vibration, electromagnetic noise, can disrupt the unified wave of the Cooper pair system, causing it to lose its quantum state. This fragility is one of the biggest challenges in building stable quantum computers. It is as if the entire choir must maintain perfect harmony, while the world around them shakes unpredictably. A single stray vibration, a breath of warm air, a tiny fluctuation, and the choir loses its note. Yet even with this fragility, the existence of macroscopic tunneling is one of the most profound discoveries of modern physics. It shows that quantum effects are not limited to the tiny and the unseen. Under the right conditions, low temperature, careful materials, precise engineering, the wave-like nature of matter can scale upward, becoming visible in the flow of current, the oscillation of junctions, and the behaviour of circuits that are large enough to hold in your hand. In recent years, experimental breakthroughs in superconducting circuits have even been honoured with the highest scientific accolades, confirming that these strange tunnelling behaviours are not theoretical curiosities, but real, measurable phenomena. Entire laboratories now operate at the boundary between engineering and quantum mechanics, sculpting devices where probability itself is a working component. And so, superconductors and Josephson junctions reveal something quietly beautiful. They show that when particles act together, their possibilities overlap and strengthen. Unity creates pathways the individual could never traverse alone. Tunnelling becomes not just a microscopic event but a collective gesture, a wave of countless electrons gliding through a barrier in perfect synchrony. In the darkness of a lab cooled close to absolute zero, where vibrations fade and matter becomes still, you will find these waves moving, silent and precise. It is a reminder that the quantum world, though often hidden, can rise up into the visible world when conditions allow. And in those moments, we glimpse the universe not as a place of rigid boundaries, but as a landscape where cooperation and possibility allow even the impossible to unfold. If you close your eyes for a moment and imagine the world inside your body, you might picture something made of movement, blood flowing through veins, air filling your lungs, cells dividing, signals travelling through nerves. But beneath these familiar motions lies a quieter world, a world far more delicate where molecules drift like dancers following steps too small for us to see. In this hidden world, the difference between healthy and unhealthy, between balance and imbalance, can come down to the slightest shift in how particles move. Modern medicine has always tried to understand and influence this tiny world. But now, as scientists look more closely, they are beginning to sense something surprising. Quantum tunnelling, the same phenomenon that lights the stars and shapes radioactive decay, may also have subtle but powerful roles to play inside living systems, and perhaps even in future medical technologies. At first glance, tunnelling seems too strange and too gentle for medicine. After all, diseases feel solid and urgent, infections that spread, cells that divide uncontrollably, tissues that degrade. Tunnelling feels like the opposite. Soft, ghost-like, a whisper crossing a barrier. Yet many of the most important processes in biology are shaped by extremely small movements. When a molecule needs to pass into a cell, when a protein needs to activate or deactivate, when an enzyme aligns a reaction just so, much of the work depends on how tiny particles behave. And when the classical pathways become too narrow or too slow, tunnelling sometimes opens a quiet shortcut. The idea of tunnelling-inspired drug delivery may sound fantastical, but the inspiration is more subtle. It does not mean that medicine will teleport through tissues or dissolve through walls the way a particle might. Instead, scientists are studying how certain barriers in the body, especially cell membranes, can briefly shift, fluctuate, or thin in ways that allow small molecules to pass more easily. A drug might not literally tunnel through a membrane, but the concept encourages researchers to design molecules that take advantage of those fleeting windows of possibility. They aim to craft medicines that slip through microgaps rather than forcing their way with brute chemical force. You can imagine a cell membrane as a flexible curtain rather than a rigid wall. Most of the time it keeps things out, but occasionally the curtain ripples, creating a momentary opening. Traditional drug design focuses on pushing through the curtain using shape and chemistry. Tunnelling-inspired design focuses on gliding through during those brief ripples, using size, timing and alignment in a way that feels almost like a dance. Beyond delivery, tunnelling plays a role in ultra-sensitive medical diagnostics, technologies that depend on detecting the faintest signals. One example involves sensors made of nanomaterials, where electrons tunnel across small gaps when biological molecules land in just the right place. These sensors act like microscopic listeners, waiting for the quietest tap, a single molecule binding, a tiny shift in charge. Because tunneling is so sensitive to distance, even the presence of a single virus particle or protein can change the electron flow enough to be detected. Think of it like listening for a raindrop falling on a sheet of metal. If the metal is large and heavy, the sound disappears. But if the sheet is thin and perfectly tensioned, the faintest drop becomes a clear, recognizable note. Tunneling creates that kind of sensitivity. By designing sensors that operate at the edge of possibility, researchers can detect biomarkers earlier, faster, and with gentler methods than traditional systems. And then there is imaging, another frontier where tunneling quietly influences ideas. While no medical imaging device literally uses tunneling to construct pictures of organs or tissues, the concept has inspired techniques that rely on extremely small energy changes. In certain scanning devices like magnetic resonance systems, the way particles align or flip states can be influenced by ideas drawn from quantum behavior, including the recognition that particles can shift states not by climbing energy barriers, but by being coaxed through them. This softens the energy requirements and leads to less invasive imaging methods. Some researchers also explore the idea of quantum biology, a field still young and full of uncertainty, where tunneling may help explain phenomena like enzyme efficiency, photosynthesis, or even the ability of certain animals to sense magnetic fields. While many of these ideas remain under investigation, the possibility that quantum behaviors contribute to biological precision is opening doors to new ways of thinking about medicine. The caution here is gentle but necessary. Tunneling is not a magical cure or a dramatic biological engine. It is a subtle influence, a guiding breeze rather than a gust. But medicine is often shaped by subtleties. A tiny shift in reaction speed can determine whether a drug metabolizes safely. A small improvement in how molecules move can reduce side effects. A quiet enhancement in signal detection can save a life through early diagnosis. Perhaps the most intriguing future direction involves combining tunneling-sensitive electronics with biological environments. Imagine a thin device, no larger than a grain of sand, placed in the bloodstream. It senses molecules by allowing electrons to tunnel across tiny gaps. It reports data without needing large amounts of power or invasive procedures. It could detect early signs of disease or monitor how a medication behaves in the body. This is still a dream, but not an impossible one. What makes this direction compelling is the same thing that makes tunneling compelling in physics: its extraordinary sensitivity. A barrier slightly thicker or thinner can alter tunneling dramatically. A molecule landing on a surface can open or close the pathway. A biological environment that shifts from warm to cool, from acidic to neutral, can reshape the tunneling landscape. These small changes become signals, whispers translated into measurable differences. In all of this, tunneling serves more as a teacher than a direct agent. It teaches us that the body is full of subtle energy landscapes, that barriers are not perfect walls, that processes depend not only on force and impact but also on timing, alignment and possibility, and it encourages us to imagine new medical tools and approaches that move gently, that read the body with the softest touch instead of the harshest. As you sit here listening, your own biology is quietly guided by similar principles. Protons shifting in enzymes, electrons moving through proteins, molecular reactions proceeding through narrow corridors. Life works not through brute force, but through exquisite precision. And tunneling tells us that precision often comes from allowing the smallest possibilities to flourish. Medicine at the edge of the impossible is not about breaking rules. It is about understanding where the boundaries soften and learning how to work with that softness to heal, sense, and protect. In that sense, tunneling is not only a phenomenon of physics, it is a reminder whispered from within the smallest particles of our bodies that many pathways remain hidden until we learn how to look with gentler eyes. If you think about how you're listening to this right now through a phone, a tablet, a laptop, you're living inside a web of decisions made by electrons. Every message you send, every picture you see, every sound that reaches you travels through tiny circuits carved into metal and silicon. These circuits are made of switches, little gates that let electrons flow or hold them back. For decades, these switches have been shaped by classical physics, obeying the rules of on and off, open and closed, as predictably as a light switch on your wall. But as we've explored, the quantum world does not always honour such strict boundaries. In that world, barriers may soften, electrons may drift through walls, and possibilities may overlap. So as computers grow smaller, denser, and more ambitious, classical rules become increasingly strained. The question emerges: what happens when our machines reach the size where tunneling is no longer a minor inconvenience but a dominant feature of how electrons behave? This is where the future of computing meets the soft, ghost-like logic of tunneling. To begin, imagine that each transistor, the fundamental switch inside a classical computer, is like a small hill between two valleys. In one valley the switch is off, in the other it is on. In classical physics, a particle must climb the hill to move from one valley to the other. But when the hill becomes very thin, tunneling allows the particle to slip quietly through, even when it shouldn't. This leads to leakage, noise, and loss of control, hazards for traditional computing, where reliability must be absolute. But instead of fighting the quantum world, an entirely different approach asks, what if we build a computer where electrons are supposed to tunnel? This question lies at the heart of quantum computing. In a quantum computer, the basic unit of information, the qubit, does not sit firmly in 0 or 1. Instead, it can exist in a mixture of both states at once. And many ways of creating qubits rely on tunneling between two energy landscapes. Instead of a tiny hill separating valleys, imagine a particle poised between them, partly in each, like a delicate balance of possibility. You might picture it as a tightrope walker suspended between two cliffs, able to lean subtly one way or another without falling. In some designs, a qubit's two states correspond to two different shapes of a wave function, two patterns of how the particle's presence spreads. The particle can tunnel between these patterns, allowing its state to shift, blend, or combine in ways that classical bits cannot replicate. The computer does not compute by flipping switches, but by guiding a landscape of probabilities, letting certain outcomes strengthen and others fade. To make this concrete, imagine a ball placed in a bowl that has two dips in its base, two shallow hollows separated by a tiny ridge. Classically, the ball sits in one dip or the other, but quantum mechanically, the ball becomes a wave that spreads across both dips. Tunneling determines how much of the wave leans into each hollow. This lean becomes the qubit's state, neither pure 0 nor pure 1, but something softer and richer. When these qubits work together, they can explore many possibilities at once. Instead of testing one path at a time, a quantum computer allows multiple paths to coexist temporarily, like many ripples overlapping on a pond. This ability to explore multiple outcomes enables quantum computers to solve certain problems far more efficiently than classical computers. Problems such as simulating molecules, optimizing vast systems, or breaking certain mathematical codes. But tunneling does not only shape the on state of qubits, it is also essential for how quantum computers perform operations. When you apply a pulse of energy to a qubit, say a gentle electromagnetic nudge, you are reshaping its energy landscape. Hills lower, valleys rise, and the wave that represents the qubit shifts in response, tunneling into new configurations. The entire computation becomes a guided evolution of wave patterns, sculpted by subtle pulses rather than macroscopic switches. This dependence on delicate quantum behavior is both a strength and a challenge. It allows incredible computational power, but it also means qubits are fragile. A stray vibration or a warm breath of air can disturb the landscape. A tiny fluctuation in temperature can cause the qubit's wave to collapse into a single state, losing the delicate mixture that carried the computation. This collapse, known as decoherence, is one of the biggest challenges in quantum computing today. To avoid it, qubits must be shielded from the outside world, often cooled to near absolute zero so that their wave-like nature remains coherent and stable. Yet even with this fragility, researchers have made astonishing progress. Superconducting qubits, trapped ion qubits, and semiconductor qubits all use tunneling in one form or another. Some qubits rely directly on electrons tunneling across tiny barriers. Others rely on the tunneling of entire groups of particles moving as a single quantum wave. In all cases, tunneling becomes a way to navigate the energy landscape, a way to move smoothly between states that would be unreachable in classical physics. There's another frontier where tunneling may shape computing: secure communication. One of the promises of quantum technology is the ability to detect eavesdropping, because measuring a quantum state inevitably alters it. In certain systems, tunneling could contribute to security by creating delicate states, whose presence or absence depends on finely tuned probabilities. Any interruption would disturb the state and reveal the attempt at intrusion. This is not yet a mainstream technology, but the conceptual groundwork is being laid by experiments that explore tunneling-based sensors and transmission pathways. In all of these developments, we can see a shift in how technology views barriers. Classical computing treats barriers as absolute. A transistor is open or closed. The goal is to make barriers strong enough to control the flow of electrons, but quantum computing sees barriers as sculpted landscapes, places where the height, width, or curvature determines how waves evolve. Instead of stopping particles, the goal becomes shaping their probability. It is a profound change, from thinking of electrons as marbles travelling along rails to seeing them as ripples that move with the softest guidance. In this world, computation becomes less about pushing and more about tuning, less like building a machine and more like conducting a symphony. As you listen, you may notice how gently these ideas unfold. Quantum computing is not loud or forceful. It is quiet. It is subtle. It is built on the faintest whispers of probability. And tunneling, this strange crossing of impossible boundaries, teaches us that even in technology, progress may come not from breaking walls, but from learning how to let waves flow through them. In the small world of atoms and electrons, walls are not rigid. They're invitations to shape possibility. And computing, at its most advanced edge, is learning to move within that softness, transforming probability into a tool and letting the impossible shimmer into reality. If you imagine the world on a human scale, materials feel straightforward. Wood feels solid. Metal feels cold. Glass feels smooth. Each substance seems to have a fixed character, something you can sense with your fingertips. But at the quantum scale, materials become landscapes of hills, valleys, bridges, and shadows. Electrons drift across these landscapes like travelers searching for paths, and the structure of the material determines which routes are open, blocked, or softened by possibility. When scientists design materials at this tiny scale, They aren't carving shapes the way a sculptor carves stone. They're shaping probability itself. This is the world of engineered nanomaterials, materials built not from big blocks or fibres, but from arrangements of atoms so carefully placed that they guide electrons like invisible rivers. In this realm, tunnelling becomes a tool rather than an accident. It becomes a way to construct new pathways, new behaviours, new properties, and these properties often feel ghost-like, electrons appearing where they shouldn't be able to go, slipping through barriers designed to contain them, gathering in places that would be forbidden in a classical world. One of the clearest examples of this is the quantum dot, a tiny particle so small that it traps electrons in a confined space. You can think of a quantum dot as a small glowing island in the vastness of a sea, a place where electrons can linger, bound not by walls of stone but by boundaries formed through size and geometry. When electrons are confined within such an island, their energy levels become discrete, like the notes of a musical instrument rather than the continuous hum of background noise. And because quantum dots are so small, electrons often tunnel between the dot and nearby regions, slipping through narrow boundaries created by the shape of the material. To imagine this, picture a hummingbird hovering between two flowers. Each flower is like a quantum dot. The hummingbird's wings beat so fast that it can dart from one flower to another in an instant, not by flying in the usual sense, but by almost flickering from one bloom to the next. Electrons and quantum dots behave with similar agility. If the dots are close enough, the electrons' waves may overlap, allowing tunnelling to occur between them. This tunnelling helps determine how the material conducts electricity, emits light, or responds to external signals. In some materials, scientists intentionally arrange quantum dots in chains or clusters, creating artificial molecules where electrons tunnel from one dot to another in patterns that can be tuned with extraordinary precision. These structures behave like musical chords made of probability, combinations of states that produce unique optical or electrical properties. But quantum dots are only one part of the story. Other engineered materials use layers so thin that they're only a few atoms thick. In these layered materials, like graphene or stacks of two-dimensional sheets, electrons behave as if travelling through an intricate maze. Tiny gaps, twists, and overlaps between layers act like tunnels, doorways, or bridges for electrons. If one layer is rotated slightly relative to another, the resulting pattern can amplify or suppress tunnelling in surprising ways. Scientists call these moiré materials, named after the rippling patterns they resemble, and they are full of hidden pathways where electrons drift in ways that redefine how we understand conductivity. In these structures, tunnelling does not just help electrons move, it defines their identity. Electrons can spread across layers, forming waves that extend through the entire material, and when these waves resonate in just the right way, the material may become superconducting, insulating, or perfectly conducting, depending on subtle shifts in geometry. Rotation of one atomic layer by a fraction of a degree can turn a material from a good conductor into something almost magical. You can picture this as a pair of lace curtains overlapping. Tilt one curtain slightly, and the pattern of holes changes. Some holes line up, opening wide windows for light. Others misalign, creating regions where the light dims. In moiré materials, the holes are like pathways for electrons. When the patterns align, tunnelling becomes strong. When they misalign, tunnelling fades. Scientists learn to tune these patterns, shaping where electrons can flow. This level of control leads to new frontiers. In some nanostructures, researchers create intentional barriers, thin ridges of energy that electrons have to tunnel through. These barriers act like gates in a garden. They don't fully block the path. They simply force the electron to pause, consider, and then pass through by possibility rather than force. By adjusting the height and width of these gates, scientists shape how electrons move, how quickly currents respond, and how the material interacts with light. Imagine standing in a quiet garden at dusk, with small stone archways guiding your steps. Some arches narrow, others wide. Some require you to duck slightly. Others invite you through without effort. Your movement is shaped by their design. In engineered materials, electrons move through similar landscapes, guided not by stones but by fields, geometries, and probabilities. This guidance becomes crucial in devices where tunneling determines performance. In certain sensors, electrons tunnel through tiny gaps created between metallic nanoparticles, allowing the device to respond to minor changes in pressure, chemical presence, or temperature. In photovoltaic cells, tunneling helps carriers escape from one region to another, increasing efficiency. In light-emitting diodes built from quantum dots, the interplay of confinement and tunneling determines the brightness and colour of each tiny pixel. All of this reveals an elegant truth. At small scales, materials behave less like objects and more like environments. They become terrains where waves explore, reflect, tunnel, and settle. Designing such terrains means designing the rules by which electrons move, and when those rules are sculpted with care, the result is a material that can guide electrons the way a river guides water, through channels that feel natural, inevitable, and softly shaped. In this way, tunneling becomes not just a phenomenon to understand, but a tool to wield. It is a bridge that can be widened or narrowed, raised or lowered. By adjusting the structure of the material, it is an invisible thread woven into the fabric of nanostructures, influencing how they function even when the changes are too small to see. As we drift quietly through these ideas, it becomes clear that engineered materials are more than collections of atoms. They are architectures built for waves, landscapes where electrons do not collide or clatter but glide, fade, and reappear. They are reminders that the universe's smallest actors respond not only to force, but to form, not only to command, but to invitation. Designing materials that guide ghosts, these faint quantum travellers, is one of the most delicate forms of craftsmanship humanity has ever attempted. And in their softest movements, these electrons quietly teach us that even in the solid world, the foundations of matter can be shaped by the gentle curves of possibility. If you rest your hand on the nearest wall, wood, concrete, plaster, whatever surrounds you, you feel something solid, something unmoving, something certain. It seems absolutely true that the wall is there, that you are here, and that the two of you will never slip through one another. The world feels built from firm boundaries. Walls keep rooms separate. Floors keep us grounded. Objects stay where they are placed unless we move them. Yet everything in the wall, every atom, every electron, every nucleus, is governed by the same quantum rules that allow particles to slip through barriers. Every particle in your hand is governed by the same rules too. So why don't you drift through the wall the way a proton might slip through a barrier in the sun? Why doesn't your entire body tunnel through the surface beside you during one of those quiet midnight moments when you lean against it? The answer lies in scale, structure, and something known as decoherence. A soft but powerful idea that shows how the quantum world blends into the world of our daily experience. To begin, imagine a particle tunneling through a barrier. When a single electron or proton tunnels, its wave-like presence presses into the barrier, fades rapidly, and leaves a faint trace on the far side. If the barrier is thin enough, that faint trace becomes meaningful. The particle may appear there. For something this small, tunneling is not only possible, it's common. But your body is made of countless particles, an uncountable number of atoms arranged in complex structures. Each atom contains electrons, protons, neutrons, all interacting with one another and with the environment. For your entire body to tunnel through a wall, every particle in you would need to tunnel simultaneously and coherently to the exact corresponding positions on the other side. A staggered or partial tunneling event wouldn't work. Your body must arrive intact, atoms aligned exactly as they were before, just in a new location. To understand why this is essentially impossible, imagine a choir with billions of voices. If even a handful of singers fall out of sync, the harmony collapses. Now imagine that every member of that choir must leap across a wide river at the exact same moment, landing in perfect formation on the opposite bank. If even one singer hesitates, or jumps too early, or veers slightly to the side, the entire formation is broken. In the quantum world, your body's like that choir, but instead of billions of voices, it contains many trillions upon trillions. Every voice must tunnel in perfect unity for a macroscopic tunneling event to occur. The probability of this happening is so unimaginably small that even if the universe lived for a length of time far greater than its current age, the chance would still be effectively zero. Not zero in principle, just so close to zero that the universe would never witness it. This leads us to decoherence, the process that separates the quantum world of possibility from the classical world of solidity. When a quantum system is isolated, like a single electron floating in near-perfect vacuum, it can maintain a delicate state of superposition. Its wave spreads, it tunnels, it behaves like the soft mist we've described. But when a system interacts with its environment, air molecules, light, heat, vibrations, it loses that delicacy. The wave-like possibilities collapse into definite outcomes. This happens extremely fast for large systems. Every particle in your body is constantly interacting with surrounding particles, exchanging energy, heat, vibrations. The moment these interactions occur, the system becomes classical. Decoherence sets in. Quantum possibilities narrow. The world becomes solid. Think of decoherence as a gentle rain falling on a pond. A single raindrop might create a clear ripple, but if countless raindrops fall constantly, the surface becomes chaotic, losing any trace of the original ripple. Similarly, individual quantum behaviors get lost in the noise of countless interactions. Your body is a storm of such interactions, so is the wall. Still, another thought lingers. Even if the entire body cannot tunnel, could larger objects than electrons tunnel? Could a molecule tunnel? A virus? A grain of dust? The answer is yes, but with strong limitations. Larger objects can tunnel, but the probability falls sharply as the object grows more massive or more complex. The wave describing a large object is incredibly narrow and tightly defined. It does not extend into barriers with the same reach as a small particle. As an object becomes larger, its wave behaves less like a soft cloud and more like a sharply drawn point. Possibility shrinks, certainty grows. This brings us to an optional lens through which some physicists interpret tunneling, the many worlds interpretation. In this picture, offered not as a fact but as a gentle conceptual bridge, tunneling is seen as a branching of possibilities. In one branch, the particle remains on its side of the barrier. In another, its wave appears on the far side. The act of tunneling becomes one of many stories that unfold simultaneously, though we observe only one. This perspective reminds us that what feels like a single path through time may actually be one thread in a vast tapestry of parallel outcomes. Under this view, macroscopic tunneling fails not because nature forbids it, but because the overwhelming weight of probability favours the branch where large, complex systems remain on their original side of the barrier. That is the version of the world we inhabit, That is the version we experience. Walls stay walls. Bodies stay where they are. The quantum wildcard becomes buried under layers of classical certainty. There is a strange beauty in this. The same universe that allows electrons to slip through barriers also shapes matter into stable, reliable structures. Solidity and ghostliness are built from the same rules. It is the context, the number of particles, the extent of interactions, that changes the expression. Determinism, too, becomes softened in this light. Classical physics imagines a world where the future is locked in, like a train following rails. Quantum mechanics introduces possibility. Walls that are not absolute, particles that find unlikely paths, events that unfold from probability rather than strict cause and effect. And yet this does not turn the world into chaos. It makes the world gentle, flexible, capable of both structure and surprise. So the next time you lean against a wall, you might remember that the atoms in your hand are surrounded by waves of probability, that the surface you feel solid beneath your skin is a lattice shaped by forces and possibilities, not fixed boundaries, and that your inability to tunnel through it is not a failure of the rules, but a natural consequence of being made from countless quantum pieces woven into a coherent whole. Particles tunnel through walls because their existence is soft, spread out, and governed by possibility. You do not tunnel through walls because your existence is vast, intricate, and deeply entangled with your environment. Each form of being follows the same fundamental rules, expressed at different scales. And in that simple distinction lies the reason the microscopic world glows with impossible journeys, while the macroscopic world holds steady, giving us the stability we need to live, breathe, grow, and wonder. If you sit quietly for a moment, letting the room soften around you and your breath become steady, you might feel as though the universe is something solid, something fixed, something that exists in clear, definite pieces. Walls are walls, floors are floors. Stars sit in their steady places, glowing across the long darkness. Everything seems arranged, predictable, and orderly. But after walking through the strange world of tunneling, we begin to see that the universe is not built from certainty. It is built from possibility. Every barrier that seems firm from the outside is, at the deepest levels, a region of fading probability. Every particle we think of as fixed in place is really a soft wave of presence. Every solid thing is a choreography of countless quiet decisions made by the smallest pieces of reality. Tunneling is a gentle reminder of that, a reminder that, at the smallest scales, boundaries are not absolute. They're gradients. They're invitations for possibilities to stretch, fade, and sometimes cross. And through these crossings, everything we know, light, matter, chemistry, life, unfolds. To see the universe in this way is to let go of the idea that reality is a rigid structure. Instead, it becomes a landscape of hills and valleys, barriers and openings, all shaped by the way waves of possibility interact. Every atom is a little world of these landscapes. Every molecule is a gathering of them. Every star is a furnace lit by them. And every living cell is a tapestry woven from trillions of these tiny crossings. Some people find this thought disorienting, others find it comforting. After all, we live in a world that appears so stable that it is easy to forget how unlikely our existence truly is. The fact that protons can tunnel close enough to fuse gives us the sun. The fact that alpha particles can tunnel out of nuclei gives us the heavy elements that make planets and bodies. The fact that electrons can tunnel across thin landscapes gives us chemistry, electronics, and some of the most delicate reactions inside our own biology. Life itself, your life, here in this moment, depends on countless ghost-like journeys happening inside you. Without these improbable crossings, nothing would breathe or grow or think. You would not feel the air against your skin. You would not hear a voice soothing you towards sleep. You would not be here. When we say the universe is a landscape of possibility, we do not mean that anything can happen at any moment. Possibility is shaped by structure. Probability is sculpted by the energy landscapes of matter. Most of the time, the universe rests in stable patterns shaped by overwhelming likelihood. That's why walls feel solid, why planets stay in their orbits, why you remain anchored to the floor rather than drifting into the air. But beneath this stability lies a soft underlayer where small events unfold according to different rules, quantum rules that allow the improbable to happen, just often enough to sustain reality. Consider a simple thought. Nothing is ever fully blocked, only deeply unlikely. A barrier that looks impenetrable in the classical world is, at the quantum level, merely a region where the wave fades quickly. A system that seems fixed may still allow faint traces of other possibilities. A state that seems final may still harbour a tiny chance of transformation. This does not mean we should expect dramatic tunnelling events in our everyday lives. It means that the universe is gentle in how it enforces boundaries. It allows nature to adapt, evolve, and flow without rigid walls. It allows stars to burn. It allows chemistry to be rich and varied. It allows matter to rearrange itself over eons. It allows life's delicate reactions to proceed even when energy is scarce. In philosophical moments, some people see tunnelling as a metaphor for their own lives, a reminder that obstacles, no matter how thick they appear, sometimes have hidden paths, that even the most daunting barriers may not be absolute. That change often comes not from smashing through walls, but from allowing yourself to explore the quiet, improbable routes around or through them. This is not scientific advice, just a reflection, like watching light shimmer through leaves on a windy day. But many have found comfort in the idea that possibility lives even inside the impossible. Some interpretations of quantum mechanics go further. The many worlds view, for example, imagines that every quantum event, every tunnelling, every shift in probability creates a branching of realities. In one branch, the particle remains where it is. In another, it appears on the far side of the barrier. Reality becomes a vast tree of branching outcomes, most of which we never perceive. We inhabit one branch, but the tree extends beyond what we can see. Whether or not you embrace this view, it suggests something gentle about the universe, that what seems like a single path may actually be one among many, that the world is not built from absolute determinism, but from a tapestry of overlapping possibilities. Each moment contains more pathways than the one we witness, and tunnelling is a small, constant example of this. The quiet acknowledgement that nature allows multiple possibilities to coexist, even if only one becomes visible to us. As we drift toward the end of this journey, the world might feel different, not less real, but more spacious, more flexible, more infused with softness. The solid wall you touched earlier is still solid, but now you know it is built from particles whose nature is far gentler than its surface suggests. The light in your room is still warm, but now you know it began as a tunnelling event in the heart of a star. Your body is still grounded, but now you know that inside you, trillions of ghost-like shifts are happening quietly every second. Reality is not a rigid box. It is a living field of possibilities, structured, shaped, but never entirely fixed. And so, as we close our exploration of tunnelling, perhaps you can imagine the universe not as a machine, but as a vast ocean with waves moving softly across it. Some waves rise, some fall, some slip quietly through narrow channels, shaping the world in ways we never see directly. And through all of it, You are part of this gentle movement, made from these same waves, living inside this same landscape. The barriers in your life, like the barriers in physics, may not always be absolute. Some are thick, some are thin. Some are merely regions where your own possibilities fade for a time before brightening again on the other side. And sometimes the smallest step forward, taken with patience, softness and curiosity, is enough to let a new path appear. As you settle into the quiet that follows, may the world feel just a little wider, a little softer, and filled with more hidden pathways than you once imagined.